Hello and welcome to the NPTEL online certification course on semiconductor devices for next generation field effect transistors, more than more, a physics perspective, and this is lecture number 45, and in this lecture we will be following nanosheets FET. So, the overall uh, structure is gate all around FET for the sub 5 nanometer node devices. We have already taken up the basic structure of a gate all around structure. This class we will be looking into nanosheet, and then we will be looking into the process variation and some circuit aspects of nanosheet FETs. Let me introduce to you the GAA Nanosheet FET, the fabrication process flow, and then we will look into the leakage suppression techniques in nanosheet FETs. What is the meaning of a wraparound contact screen, and then we will look into the full BDI nanosheet FET. BDI is bottom dielectric isolation nanosheet FET. Now, the whole idea of giving this as a part of the lecture series was that these devices are nanosheets and CFETs will be possibly the next generation devices which will take over from FinFETs, right. So, we have already studied FinFETs and we have seen its active role in circuit modeling in circuit simulations. We now take our leap into nanosheet FETs and look at the structure of the nanosheet FET, and then from that how can we derive the circuit aspects of nanosheet FET, and how do we optimize our nanosheet FETs in such a manner that the electrical characteristics of the device are the best available to us. So, that is the whole sort of a outline, or to an extent the objective of this particular lecture which we have. Now, let us look at the nanosheet FET. Uh, till now when we were discussing with you bulk MOSFET, the bulk MOSFET was actually a planar device, which means that on the single plane itself you had the source, drain and the gate, and the gate might be of metal or polysilicon, and the metal contacts were generally made up of aluminum or copper. However, when we move to FinFETs, FinFETs for the first time was a non planar device. It was also referred to as a quasi planar device. Why? Because rather than having everything on the same plane, the gate was slightly raised with respect to source and drain, right. That added a third dimension to the overall width of the device, thereby giving the designer one more knob to play with while optimizing it, but it also added some extra fabrication steps in order to design such a FinFET with accuracy and with stability. Moving ahead in the same lines as FinFETs, scientists across the world looked into one important device, and that was also referred to as the nanosheet FETs, right. This nanosheet FET was the one which came into picture. If you look at the nanosheet FETs, let me change the color of the right. If you look at the nanosheet FETs, right, on the right hand side here you see the color scheme of various layers. Now, let me give you first this example and then we will go one by one. In this case, it is exactly the FET device. So, you do have a field effect transistor here. Now, in this case, this is your source, right, this is your drain, right, and the gate is wrapped around in all the three directions. So, if you give a potential at this particular point, the same potential is available at this point and at this point, right. Now, this source and drain, obviously there will be a metal contact which will carry it to the next stage, or from where you can give a bias to these devices to operate it in the saturation linear or nonlinear region. However, the gate, if you look very carefully, is surrounded in all sides, but the top gate is having a bit thin structure as compared to the two side gates. So, you have the gate surrounding in all the three directions, right, in this manner. However, if you look very carefully, the sheets are actually aligned in this manner, and the sheets are basically, so if you have a source and drain, the sheets are moving like this. You get the point? So, it is almost like I will give you an example, it will almost like this. So, if you have a source and a drain. The sheets are 1, maybe 2 and 3. The currents are flowing through these sheets, right, if this is source and drain. So, typically I am showing you 3 sheets here. There can be 5 sheets, 7 sheets and so on and so forth. Now, if you look at this is basically a vertically nanosheet FET, this one, right. And on the middle side, on the middle diagram, the second one is basically the cross section. So, if you cut it across this plane, you get this structure available with you, As you can see here, you have this source and drain obviously, which will carry. This is the silicon which you see here, this is the silicon. So, this all pink colored diagrams are basically silicon, right. It can be doped, it can be undoped silicon also, but it is silicon nonetheless, right, and this is the substrate. So, this whole area is basically the silicon which you see, right, and that consists of both the substrate as well as the side channel which you see. And then of course, the silicon is also available at this particular point, which takes care of the movement of charge carriers from source to drain. And if you look carefully again, then the separation between the two channel is given by TCH, and LG is the length of the channel which you see, LG is the length of the channel, this one. Now, we also insert is what is known as a spacer here, right, this is a spacer, and the spacer in our case at least is silicon nitride, right, we have used silicon nitride for spacer. Now, if you look at very carefully now the MOSFET itself, let me rub this portion, then let us concentrate, let us say we concentrate only on the second sheet here, let us suppose, right, or the third sheet, how you look at it, it's onto you. Now, if you concentrate again at this particular point, there are 2 layers of dielectric. One is the high K material, this is high K, and the brown colored is low K. Low K is silicon dioxide and the high K is hafnium dioxide. So, what you are doing, you are vertically stacking each oxide layer over each part. So, in a bulk MOSFET for example, when we were doing, you had only an oxide layer separating the inversion layer and the gate. Here we have this stacked oxide layer sort of available. Each stacking is having hafnium oxide as high K dielectric and silicon dioxide as the low K dielectric. You can also have the either way, that means you can have either silicon dioxide as the first layer and hafnium dioxide as the second layer, or vice versa, that you have hafnium dioxide as the first layer and silicon dioxide as the second layer, each one of the above. Both ways you can fabricate it, and I am assuming for all practical purposes that there is no traps involved. So, there are no traps here. So, it is perfectly ideal case and there are no traps, and it is an ideal interface which is available with all of us. You can generally ground the source, you can give a bias here VB, VDS, and that will result in the current flow in all these materials. Now, this is silicon. So, now let us come to the last schematic here, cross section here, and what I do here is I do one important point which I do is basically this brown color, it is STI which we put, which is also known as a shallow trench isolation, and this is generally done in order to isolate the device from subsequent nanosheets. So, in all of the cases you will not make a single nanosheet, right. So, on a silicon wafer you have multiple nanosheets available. However, they have to be electrically and structurally isolated from each other, so that if one nanosheet FET is in the on state, it does not allow the other to be also in the on state. So, there is less amount of interference between the two. Now, if you see very closely, this pink color is silicon through which the current is flowing, above which you have silicon dioxide followed by high K material, and then you have this metal 1 layer and then metal 3 layer and a metal 4 layer. The metal 3 layer is the most outermost layer of the metal. Metal 4 layer is basically your titanium nitride, right. Metal 3 is basically nickel silicide, right. You can also have metal 0, which is basically the metal layer, basic metal layer which you put. So, there are 3 to 4 metal layers which are associated with nanosheet FETs, at various places. Why? Because the final layer of nanosheet, which is M4, will be responsible for it to talk to the external world, right? And that's the reason this structure gives you a brief idea about that, the overall structure. So the reason for showing this slide to you was to give you an idea about how a nanosheet FET looks like when you do it on a 3D schematic, when you do a cross section, cut the plane, and so on and so forth, right? And that is how you do it. The process nowadays are very stable in nanosheet FETs. Let me come to various configurations of nanosheet FET. So what I can do is, and this is what people have been doing, is say what I can do is I can do double stacking of sheets rather than a single stack. I can do a double stacking. What you see on the rightmost side of the figure is basically a single stack. What is a single stack? There is a single, this black color which you see, this is the channel region, right? So there is a single channel available. So there are 3 channels available. What is a double stack? Double stack is you just break it into half, and therefore you have one stack here, you have a second stack here. Similarly, you have one stack here, the second stack here. What has happened is that this TSSUS is the thickness between the 2 sheets, right? This TSUS is the that is remaining constant even when you break open the device, right? However, if you look to this diagram and this diagram, the difference between them is that this is 60 nanometers long sort of width, whereas this is 50 nanometer. So the effective width has actually increased, right? And DNS is basically the diameter of the nanosheet. I can name it as the DNS, or the distance of the nanosheet to the diameter of the nanosheet. Now W effective, if you want to find out for the whole nanosheet structure, for in this case you can do it very easily. If you know this is x, if you know this is x and this is y, then each one will have a perimeter of 2x plus 2y, right? And then you multiply this into 3 because there are 3 sheets available. So it is basically 6 times x plus y, and that is what you get from it. There is a problem that the capacitance will increase in such a scenario because you have broken down the structure into smaller parts, right? And that is the reason just breaking it down into smaller multiple stacks always help is not a good idea. Now the best improvement what people have seen is keeping both the capacitance and the on current into consideration is when you use a single wide nanosheet stack, right, and constant active width of Rx into W. Now if you look at this diagram here, this diagram, then this is the active region which you see, active width of the region, and this is the total effective width. So what we have seen is the FinFET has got the least effective width for the same amount of active width, whereas if you do a single stack full active width, you get the best area, total effective area is very large here. You will also get approximately the same area, but the total active width will increase when you break it down into multiple stacks. What does it mean? Total active region in the width dimension, for example, look at the red ball here or the black sphere here. Both, if you look, you see the total effective width is approximately same, 1.3, 1.2 times the value. So it is approximately the same. But what you have paid the price when you make it, that your total active width on the silicon wafer itself has increased. Why? Because you have also been able to add this extra separation layer between the two. That increases the sort of area performance in this case. Now once we have understood now the structure of a nanosheet FET and which structure is the preferred one, the preferred one typically is the single layer structure having 3 sheets, for example. You can also have multi stacks available and have multiple layers, but the fabrication and the capacitance becomes more difficult in a sense. So let us look at the nanosheet fabrication process flow. So what we do is that we take up a initial silicon germanium silicon epi layer is done, right, and we do a sandwiching of those layer. Then what I do is we do an spacer image transfer here, SIT. Once I do a spacer, this is silicon nitride, right, Si3N4. Why we do it? We want to make the electric fields sort of get down onto the channel region, and that's the reason you want the spacer to grow. So what I do, I make it silicon nitride here, right? The golden color which you see is silicon nitride, and then you bring up, etch it away later on for all practical purposes. The point D is you do a fin etching, right? What is the meaning of fin etching? Then you start doing the etching of the fin by using a chemical process. The last stage is you do a STI. STI is basically the shallow trench isolation, wherein what you do is in the sides, on the side channel, you grow a substrate which is basically an insulator, right? When you do an insulator, what you end up having is that you try to make a separation between two active devices on the silicon platform, and that makes it separate out slightly in a sense, and they will never short when you turn on the device. So we are going from this side to this side. So we do dummy gate. Dummy gate is this one which you draw, and then you do the spacer again, right? The spacer nitride formation. Then we do an epitaxial growth of the source and drain. So this blue colored source and drain are epitaxially grown, and then we do a ILDO deposition here. I do a interface layer deposition, oxidation deposition, and then once it has been done, the dummy layer is now removed. Once the dummy layer is removed, the structure, nanosheet structure, comes into picture, right? And this fabrication process flow is almost like your conventional CMOS process flow, and that's the reason this is compatible with the CMOS process flow as an accepted in the semiconductor industry. Now, once you have done the dummy gate removal, which is here, what you are left with, what you are left with, this part, right? And then what you do, you go on etching the nanowire, release silicon nanosheet channel. You start removing it, right? What you do, you start removing it by giving chemical removal, and then we put a high K material formation here. So we do a high K material formation here. This is the high K material which you see. Then we do a chemical planarization, right? And then we finally make the contacts in the metal, which is this one, and these are the contacts which you see, right? So these are the standard techniques of fabrication process flow, and you can get it from the link which is shown in the PowerPoint presentation slide. Now let us come to an important topic of nanosheet FETs, that you are aware of the fact that when you are discussing bulk devices or bulk MOSFETs, even in subthreshold region, you did have a large amount of subthreshold leakage currents, right? And this was actually making the low power design more and more difficult. Now, similarly, in nanosheet FETs, what we do is, in order to reduce this value of the current, we do a dielectric insertion just under the source and drain. So what we do a dielectric insertion just under source and drain, right? So this is your source and drain, and this is your dielectric which you see. Once you do that, you don't allow the charge carriers in subthreshold region to go towards source and drain, because it is almost like a MOS structure now. This is a TEM image, or the transmission electron microscopic image, and this is your source drain dielectric. What it does is that it does not allow any, assume that they were not present initially, then there would be a direct flow between source and drain through region rather than this thing. So when you insert a dielectric wall, it actually reduces drastically. Now, if you look at this graph on the right hand side, then the square blocks are dielectric with source drain, under source drain, right? And you see full dielectric isolation is also given by the green rhombus, or a green square, and you can see here below the threshold voltage there is a substantial drop in the current, right, because of the reduced leakage current, when you take into consideration the dielectric under source drain region as well as full dielectric isolation. And this gives you a good amount of power saving when you actually use it for circuit modeling purposes. This is the reduction in the, or the suppression in the subthreshold leakage current. Now Let me show you another configuration of nanosheet FET, and this is known as a wrap around contact scheme, right. And this is used to maximize the contact area of the rays source and drain. See, the idea is, if a contact area is very small, and you very well know that R equals to rho L by A, then if the contact area is very small, the resistance actually starts to increase. And therefore, what we try to do is, in a wraparound contact, is that if you have a source and drain, then we wrap it all around by the metal layer, and therefore the effective area increases and the effective resistance falls down. What does it involve? It basically involves what is known as a conformal metal deposition, and we do ALD or CVD of titanium or titanium silicide. So, titanium SiX, X is a molar fraction of silicon which we use, and that is shown by this diagram here. So, this is the wrap around metal which you see here, right. This is the sheets here, these are the sheets, and this is the wrap around material. If you look at the right hand side figure here, which is normalized performance in terms of delay and normalized active power, then as the active power goes on reducing, it also goes on, the performance actually reduces, which means the delay actually increases. Why? Because then the power delay product will always remain constant, and as you go on increasing the normalized active power, your performance also increases, which basically means my tau goes on reducing. The black curve is without the wrap contact, and the red one is with wrap contact. So, you can see with wrap contact, your normalized performance is having a larger value as compared to a without wrapped contact, right. Now, this red color is basically with WAC. So, with WAC you get a better performance limits within this one, and this has been sort of experimentally proven over a period of time. Now, we also put what is known as a punch through stopper in nanosheet FETs, right. This is the nominal source drain region diagram on the left hand side, and as you move from this thing from 5 nanometer source drain to 10 nanometer deep source drain, we try to increase these source drain region more inside the substrate, right. And one is moved 5 nanometer down the substrate, and this is moved 10 nanometer down the substrate. How does it help me? It helps me to improve the leakage current, right. Now, if you look at the first graph here on the left hand side, which tells you the variation of ID sat with VG, then with BDI, which I will discuss with you later on. BDI is basically your bottom dielectric isolation. Your off currents are reduced drastically low as compared to other case, right. And in the other case, this optimization of this T1 and T2, the width, will make the device work properly. Now, the flip side of the story is that that the dopant amount in the PTS, which is split 2, can actually turn off the parasitic fin, right, and that is the problem area which you will face. Now, let us come to the last part of the understanding of this structure, and that is basically your BDI. BDI is bottom dielectric isolation, and what I do is, below source and gate, I sort of make a silicon dioxide layer, so that any charge carriers cannot move from this point to this point and vice versa. And this is known as a bottom dielectric isolation in nanosheet FET, and we do a full bottom dielectric. The cost you pay for it is basically having overlap capacitances and gate to inversion capacitances being formulated for the last gate. Now, if you look at the right hand side figure, this plots the current with respect to the gate voltage, and when you do a nominal 1 or 5 nanometer depth, the current is very low, right. So, if your BDI, so where you place your BDI with respect to the nanosheet is quite critical in understanding how much amount of off state leakage current will be actually stopped by this BDI. On the last table which you see, that if you use a BDI, I get a normalized Fmax. Fmax is the frequency of maximum frequency of operation, is increased by a factor of 1.046 as compared to your standard cells, which does not use a BDI. So, let me recapitulate what we did in this approximately few elements of this design. We looked into a nanosheet FET, NS FET, and then looked at the various structures of NS FET. So, we looked at NS FET and then we looked into various structures of NS FET. Remember, we can have multiple stacks or single stack. So, I can have multiple stack. I can also have a single stack. What are the relative advantages and disadvantages of multiple stack and single stack? Then we went for a wrap contact structure, and we saw that the resistance is much smaller, therefore, the performance is much better because your resistance is small. And since resistance is small or the area is large, rho L by A happens, and therefore, resistance is relatively smaller because area of contact is much larger in this case. After doing the structure of NS FET, we looked into BDI, which is bottom dielectric isolation, and STI, shallow trench isolation. These isolations are meant to make your off current as small as possible. So, this lecture therefore gives you a brief insight into the nanosheet FET, its structural analysis, and how does it influence the performance of a nanosheet FETs. Thank you.